Welcome back. Today we're going to talk about section 4.3. And sorry, my copy is not real dark, but hopefully when you printed yours out, it worked out just fine. Or showing up on your tablet or whatever. We're going to talk about how derivatives can affect the graph and exactly what's happening as we're looking at this. So what is going to happen is when first we're going to talk about increasing and decreasing. So when we have a slope of a tangent line that is positive, remember, a positive slope means that as x gets bigger, y is also getting bigger, positive slope. When we have a positive slope of a function, this means that meaning all of the y values as x is progressing, as x gets bigger, y is also getting bigger. Then we say that f is increasing. And when the slope of the tangent line is negative, remember that means that as x progressive, y gets smaller. So when as x is getting bigger, y is getting smaller. This means that the graph or that the function is decreasing. And to translate that into something that we can use, we say that if f prime of x is positive, meaning the slope of the tangent line is positive like we have here, then f is increasing. And then the opposite is true if f prime of x is negative, if the slope is negative, if it's less than 0, then f is decreasing. And let's go ahead and take a couple of minutes and do some examples of that, keeping that in mind. All right, so we're going to find the intervals on which the functions are increasing and when they're decreasing. So first thing I'm going to have to do, obviously, is take the derivative, the first derivative. I'm going to have to use product rule here because I have two functions of x. So derivative of x is 1 times e to the negative x plus x, and derivative of e to the negative x is negative e to the negative x. And I'm going to rewrite that as e to the negative x minus x e to the negative x. All right, and what we basically want to do is know when this is equal to 0. And then we're going to figure out its breaking point. I'm going to go ahead and factor out an e to the negative x. And I want to point out e to the negative x is always positive. And you'll note it's not equal to 0, it's just always positive. So we can actually divide that out and we end up with 1 minus x equals 0 or x equals 1. And this is called a critical value. We talked about that in another video. So what we're going to do is we're going to set up a scale. And we are going to break it up into a couple of pieces, specifically when, and these are x values. What happens when x is less than 1 and what happens when x is bigger than 1? Well, this is fairly simple. When x is less than 1, let's say 0. I plug that in here. This is, again, always positive, so I'm not going to pay any attention to it. So when x is 0, I can see I'm going to end up with positive values over here, meaning every value of x to the left of 1 is positive. Or another way to word that is the slope of the tangent line before x equals 1 is always going to be positive. And if I pick a number bigger than 1, so if I pick 2, 1 minus 2 is going to give me a negative 1. And what that is telling us are the intervals of increasing and decreasing. So what we're going to say is f is increasing, and we'll use interval notation on negative infinity to 1. Typically, we don't include the endpoints. And f is decreasing on 1 off to infinity. And so that is our actual answer. All right, let's do it again with our second function here. Again, we're going to start out by taking the first derivative. That's going to give me 6x squared plus 6x. Derivative of 1 is 0, of course. And I want to know when that equals 0. Factor out as 6x. So it looks like we're going to have two critical values in this case. I'm going to have x equals -1 and 0. These are my critical values. Meaning these are potential turning points from negative to positive slopes. So let's set up our graph again. This time we're going to have several regions to test here. And this is going to be -1, and I'm going to over-exaggerate, make that 0. And you can see this splits it up into 3 regions for us. And we want to know, is the slope positive or negative in each of these regions when we plug in x values? Well, let's test over here. Let's test when x equals -2, right? That's just to the left. So 6 times -2, -2 plus 1. That's -12 times -1, which is 12. So this tells us that the slopes of the tangent line before -1 are going to be positive slopes, meaning increasing there. We'll pick a value between -1 and 0. Let's pick x equals -1/2. And that's going to give me a -3. That's going to give me a +1/2. So that's going to give me -3/2. Now, I don't care what the number is. The point is, it's a negative value, meaning it's decreasing from -1 to 0. And we'll test a point out here. Keep it simple. And again, the number is not relevant. It's the sign. So the slopes of the tangent lines are positive after 0. So we're going to say that f is increasing on negative infinity to -1, and, or I should say, 0 to infinity. And f is decreasing from -1 to 0. Not too bad when it's easy to take the first derivative and set it equal to 0. So let's keep going. And that brings us to the first derivative test. So if f prime, maybe that's a little hard to see, f prime changes from positive to negative at c, then f has a local maximum at x equals c. If f prime changes from negative to positive at c, f has a local minimum at x equals c. Now, if the sign doesn't change at c, then f has no local extrema, meaning no local min or max at x equals c. Okay, So from negative to positive or positive to negative, that means that the slope is going to be 0 at one point. And I want to point out all the places where the slope is 0. We have right here. We have right here. And we have down here. And again, for each of these, f prime equals 0. And I want to point out that the slope of the tangent line before our 0 here f prime is positive, and even after f prime is positive. However, so here we're going from positive to negative slope. So here is our negative slope. Well, it's going to get intrusive regardless. We have a negative slope there, so f prime is less than 0. So because we're going from a positive slope to a negative slope, we're going to have a local maximum. And you can see we have a local maximum there. Here we went from a positive slope to a positive slope. That's this case down here. There's no extrema there. Over here, however, we're going from a negative slope to a positive slope. And you can see we have a negative slope to a positive slope. That's here. We have a local minimum, and we can see that local minimum right there. All right. Let's do our second example. Find the local extreme of f of x equals 3x to the fourth and so on. So first off, we need f prime. That is going to give me 12x cubed minus 12x squared minus 12x plus 12. And we'll set that equal to 0. And I'm going to take a minute and divide out the 12. Sort of a no-brainer there. And what I'm going to do, I know x cubed is a little intimidating. What I'm going to do is I'm going to factor this by grouping. Make sure you do the plus the negative. If you just put parentheses around there, that changes the meaning. Here I'm going to factor out an x squared. Here I'm going to factor out a -1. And we're almost there. I'm going to continue to factor. And we're going to end with that. And our critical values are going to be x equals -1 and 1. And that is what we were going to test. I'm going to go ahead and do that here. And let's partition that off a little. And we're going to test some values. And we're going to test them into here. Now remember, anytime you square a real number, you get a positive value back. All right, so let's test x equals -2 into here. -2 minus 1 is -3. -2 plus 1 is -1. -9 is the number. I'm only interested in the sign itself, meaning the slope of the tangent line is negative for any x value before -1. And between -1 and 1, let's use 0. It's the easiest. So this gives me -1 squared times 1, which is just a +1. And in the last region, I'm going to test x equals 2. That's going to give me 2 minus 1, which is 1 squared. And that is going to be 2 plus 1. And that is going to be 3. So you'll notice the sign did not change here. So that falls into this category. There's no local extreme here. And our conclusion, because we are going from, let's get everything in there. We're going from a negative slope to a positive slope, a negative to a positive slope. We have a local minimum. So f has a local minimum at x equals -1. We can even find that local minimum by plugging that into here. So f of -1, and I threw that in my calculator, and you get -10. So this is the minimum, the -10. And we can even write it as an ordered pair. So just to be clear, this is the local minimum, -10. Remember, the minimums and maximums are always y values. All right, moving on. Let's do another one. Got some trigonometry with this one. Very nice. Let's take the derivative. That's going to be 1 plus 2 cosine x. And they say x is only going to be between 0 and 2 pi. So I'm going to have to set this equal to 0, which means cosine of x equals -1/2. And cosine is negative in quadrants 2 and 3. And using either the unit circle or the special right triangles, we can come to the conclusion that x is going to be 2 pi over 3 and 4 pi over 3. There's actually an infinite number of them, but they've given us a limit on our domain very nicely. And let's set up our table. And I'm going to test 2 pi over 3 and 4 pi over 3. And just for a quick reference, what I'd like to do is just sort of get a decimal approximate so I can know what to test. So 2 times pi divided by 3. So again, this is just more for me knowing what to test. So this is about 2.094. And you see that one's twice that one, so I'm just going to double that times 2. All right, I'm going to do a little trick again. And I'm in the wrong mode. Needs to be function, and we need to be in radians. You need to check that every single time. And I'm going to go into here. And I'm going to type in x. I'm sorry, I'm going to type this in. 1 plus 2 cosine x. And so I'm going to pick a number less than that. Let's pick 1. So I'm going to do vars, y vars, function y1. And I'm going to evaluate that at 1. And again, I'm just looking at the sign. This is all that's important to me. So I picked a number over here, and this became positive. Let's pick a number in between. Let's pick the number 3. And it's negative. And let's pick a number over here. So let's pick 5. We're going to do vars, y1 at 5. It's positive again. All right, so our conclusion is that there is a local max, because we're going from, get both on there, a positive to a negative. So we have a local maximum, local max there. At x equals, I'm sorry, at the interval at x equals 2 pi over 3. And because we're going from a negative to a positive, we have a local minimum. Minimum at x equals 4 pi over 3. And what we can do is actually find what the local maximum is. So f of 2 pi over 3. And that is going to give us 2 pi over 3 plus 2 times the sine of 2 pi over 3. The sine of 2 pi over 3, sine is positive in quadrant 2. This is root 3 over 2, which is 2 pi over 3 plus root 3. So this is, again, our local maximum. And evaluating f at 4 pi over 3. That's quadrant 3. Sine is negative in quadrant 3. And again, this is a local minimum. This is the y value. So this is the actual local minimum. And we have local minimums at x equals this. And so when we evaluate it, we get the y values. Super cool stuff. So that's the first derivative, how it affects the graph. Let's now talk about how the second derivative affects the graph. All right. So this did not come through very well. See if I can trace this well. Not so well, but that's okay. And this one is here and here. And the function looks like this. That's function g. All right. So what does f double prime say about the graph? And graph A and B show the graphs of two increasing functions. So meaning the slope of the tangent line is positive in both cases, but they look differently. And so we have a definition. If the graph of f lies above all of its tangents, so when we put in a tangent, oh, we actually have them here. So here, the graph is above it. Here it's below, pardon me. If it's above, that's here. If it's above, then we say that it is concave upward. So again, if the tangent is above the graph, then it's concave upward. If the tangent is below the graph, like we have here, then we say it's concave downward. And It's concave upward if f double prime is positive. It's concave downward if f double prime is negative. And we can see with this big graph down here, we're concave downward here, meaning it's concave downward versus upward. So concave downward here, and then right here, things change. It's concave downward, and then it changes to concave upward. And then from here, it's now concave downward. So these points right here mark where it's changing from downward to upward. And then here we're concave upward again. So D is a point, although it's a corner. This is another corner. You can see it's concave upward. It's still concave upward. And then it changes here from concave upward to concave downward. Here we have a local maximum. That's the first derivative. Local minimum, and so on. All right, and yes, we are building up to a giant graph coming up on the last page. All right, definition. A point P on a curve y equals f of x is called an inflection point. If f is continuous there and the curve changes from concave up to concave down or from concave down to concave up at P, then we have the inflection point. And we are going to do example 4 here to identify the concave upward, concave downward. So I'm going to need my derivatives, 2 of them actually. F prime of x is e to the 1/2 x squared times x. And actually, this is hard to see with this function. That's a negative, so that's a negative x actually. And my second derivative, I have to do the product rule. So I get negative e to the negative 1/2 x. That's going to be minus x e to the negative 1/2 x times negative x again. I'm going to factor out a negative e to the negative this here. And I'm going to be left with, notice that becomes plus. So when I factor a negative one of those out, this is going to become 1 minus x squared. And we want to know when this equals 0. And I want to point out once again, this function here is always positive, negative in this case. All right, so our inflection points are going to be at x. So the inflection points are going to be at -1 and 1. This is -1 and 1. And we'll partition those off. So let's do at x equals -2. -2 squared is 4. 1 minus 4 is negative. That's going to be a negative times a negative, which is going to give me a positive here. At 0, that's going to be a +1 times a -1. So that's going to be a negative here. and this is at x equals 0, and at x equals 2. Notice the same thing's going to happen here. 2 squared, so 4. 1 minus 4 is negative times a negative is going to be positive. So what that is telling us is that here it's concave upward, here it's concave downward, and here it's concave upward again. So our answer is f is concave upward on the interval negative infinity to negative 1 and 1 to infinity, and f is concave downward on negative 1 to 1. All right, we are to the last page, and then we're going to do a big graph. And here we have the second derivative test. So this says, it's a little hard to read, if f prime of c equals 0, so we're at a critical value, and if double prime of c is positive, then f has a local minimum at c. So f double prime, if it's positive, that means it's concave upward, and concave upward means that it's going to have a minimum. Right, so if our function looks like this, it's concave upward, then we're going to have a minimum. Same thing for part B, but if it's this is a typo, this should be negative. If f prime of c, the critical value, is 0, and if double prime of c is negative, then f has a local maximum at c. Be sure to change that. This should be f double prime of c is less than 0. All right, so here we are to the big one. We're going to find everything out about this that we can. Let's start out with the x-axis, the intercepts. The x-intercepts is when x to the 4th minus 4x to the 3rd equals 0. So we have x-intercepts at x equals 0 and 4. That's going to make up the points 0, 0. And when I plug in 4, so 4 raised to the 4th. Oh, no, we already know it's going to be 0. Sorry. 4, 0. I was going to show that. So here are x-intercepts. This is just where the graph crosses the x-axis. So let's now find our critical values so that we can see where our local minimums and maximums are. So f prime of x is 4x cubed minus 12x squared. So factor 4x squared out, and we are left with x minus 3. These are our critical values. And we already know, so we have a critical value at 0, 0, and we have a critical value at 3, and let's plug that in. Let's see what we get. 3 raised to the 4th power minus 4 times 3 raised to the 3rd power. Negative 27. So we're at 3, negative 27. We may have to fudge that one a little. And let's determine if these are extrema at all, and if they are extrema, if they're minimums or maximums. So we're going to test 0 and 3. All right, so let's test negative 1 here. And it doesn't matter what I put in there, that'll always be positive. Can you see negative 1 minus 3 is going to give me negative? negative here. And let's pick, so we picked x equals -1. Let's pick x equals +1 now. 1 minus 3, again, that's always positive. 1 minus 3 is still negative. So there's no extrema at 0. Let's pick something after 3. Let's pick x equals 4. And you can see positive times 4 minus 3 is a +1. So here we're going from a negative slope to a positive slope. That means we have a minimum, a local minimum here. All right, let's do our second derivative and continue analyzing this. See, we'll talk about its concavity. So I'm taking the derivative of the first derivative, right? So that's going to be 12x squared minus 24x. Where's that equal to 0? Well, let's factor out a 12x. So our inflection values are at 0 and at 2. And let's see what our points are. Again, we already know 0, 0. Let's see what happens at 2 when we plug it into the original. So 2 raised to the 4th power minus 4 times 2 raised to the 3rd power, -16. So this is at 2 -16. And let's see what's going on here for our concavity. Again, we're testing here. So if we test x equals -1, say, let's see what happens. That's going to be a negative there. -1 minus 2 is -3. So that's going to be a negative times a negative. This means it's concave upward before 0. Let's pick x equals +1. Positive there. 1 minus 2 is negative. So that's a positive times a negative. That means it's negative. That means we're concave downward from 0 to 2. And then after 2, let's pick x equals 3. +3, so that's going to be positive. 3 minus 2 is 1, so it's a positive times a positive. Next to positive, so we're concave upward again after that. Whew. All right, now we're going to actually graph this thing using all of the data that we have here. So let's push that up a little. All right. All right. So 0, 0 is a very important point on this one. We know at 0, 0, it's crossing the x-axis. We also know it's going to be crossing at x equals 4. I'll put that way out here. We know at 327, we have a local minimum. So I'm going to mark this as, I'll call this -27. This is not going to be to scale, obviously. And at -16. And let's mark this up. So halfway will be 2. All right. So before 0, 0, we are concave upward. And the slope of the tangent line is negative, which means it's going to be doing that. At the point, notice it's concave upward. And then from 0 to 2, it's going to become concave downward. And that's going to be at 2 -16. This is going to be concave downward. And then down here at 3, -27. And we're concave downward from 0 to 2, and then it changes to become concave upward. And then it shoots back up through 4. Ooh. So you can see concave upward, concave downward, concave upward at 2, -16. We have a local min. At our 3, -27, which is expected. And then we have another x-intercept at 4. There's a lot going on with that graph. A lot going on with this lesson, actually.